Quantum Electrodynamics, or QED. What is it? Well, it says it all in its name. Q tells us it is related to quantum. ED tells us it is about the motion and interactions between electromagnetic forces. Classical physics uses field forces such as gravity, which is associated with the gravitational field, and electromagnetism, which is associated with an electromagnetic field. In these two cases, the field imparts the force on an object which generates acceleration in that object according to force equals mass times acceleration. Quantum theory redefines the idea of field forces and suggests that these forces could be explained as interactions between particles. The first step in discovering QED was made by Paul Dirac in 1928 when he successfully combined quantum mechanics and Einstein's theory of special relativity. Since light, made of photons, is a subject of quantum theory, this makes quantum electrodynamics a mixture of quantum theory and special relativity. It turns out that Feynman's diagrams are the easiest to understand. They are visual representations of mathematical expressions and equations describing the behavior of subatomic particles in quantum electrodynamics. So, what if you wanted to calculate how two electrons scatter when you shoot them at one another? According to classical physics, an electric field and some repulsion will push the two electrons apart. However, in quantum electrodynamics, the electric field is now quantized. What does that mean? It means that the electric field is now made of discrete photons. Therefore, the correct way to think about this problem is to visualize a photon being transmitted between both electrons. The electrons then recoil, another photon is transmitted between the two electrons, and then the electrons separate. These photons are called virtual photons. These photons are virtual because they only exist temporarily, unlike particles which make up ordinary matter. This is what Feynman's diagrams show us. The wavy lines represent photons, while the straight lines are electrons, and the vertices where the electrons and photons meet are where the photons have been absorbed or emitted. There can be many different scenarios for the interactions between these particles, and many related Feynman diagrams as well. For example, we can have one photon being emitted by each electron. The photon could temporarily turn into an electron, and while the exchange of the photon is occurring between electrons, one of the electrons could exchange a photon with itself. QED is also the basis of atomic interaction with light, so anything to do with photoluminescence. QED might also become more relevant in future technologies that employ higher energy magnetic and electric fields than we currently use. Therefore, the future of technology is in the hands of quantum mechanics and the understanding of topics such as quantum electrodynamics.